Atoms are the building blocks of our universe. They are the fundamental units that form the basis of all matter. They are tiny particles that make up everything we see and touch, from the air we breathe to the ground we walk on. Nuclear reactions involve these atoms and the incredible forces within them. These reactions can release or absorb vast amounts of energy. There are two main types of nuclear reactions: fission and fusion. Each of these processes has unique characteristics and implications. Fission is like splitting wood for a fire. It involves breaking a large atomic nucleus into smaller parts. Fusion, on the other hand, is like igniting the fire itself, a much more powerful process. It combines smaller nuclei to form a larger one. These reactions involve the atom's nucleus, its dense core. The nucleus is where the majority of an atom's mass is concentrated. The nucleus contains protons and neutrons bound together by immense forces. These forces are known as the strong nuclear force. Fission breaks apart these bonds, splitting the atom. This process releases a significant amount of energy. Fusion forces atoms together, overcoming their natural repulsion. This process also releases energy, but in even greater quantities than fission. Both processes release tremendous energy, shaping our world in profound ways. They have the potential to provide vast amounts of power, but also pose significant risks if not managed properly. Imagine splitting a tiny atom, releasing a burst of energy. That's fission. In simpler terms, fission is like splitting a heavy atom into lighter ones. This splitting releases a tremendous amount of energy. Think of it like a domino effect. A neutron strikes a large, unstable nucleus like uranium-235. This impact causes the uranium atom to split, releasing energy and more neutrons. These neutrons then hit other uranium atoms, causing them to split as well. This chain reaction continues, releasing a tremendous amount of energy in the process. This energy can be harnessed for various uses, most notably in nuclear power plants. Fusion, on the other hand, is the process that powers the stars, including our sun. Fusion involves combining or fusing light atomic nuclei to form a heavier nucleus. This process releases an even greater amount of energy than fission. The most common example of fusion occurs when two isotopes of hydrogen, deuterium, and tritium fuse to form helium. This reaction requires incredibly high temperatures and pressures, like those found in the core of the sun. Fusion has the potential to provide a nearly limitless source of clean energy, though achieving it on Earth is a scientific and engineering challenge. Section 4. Fission versus Fusion, a tale of two reactions. In this section, we delve into the fascinating world of nuclear reactions, exploring the fundamental differences and similarities between fission and fusion. Fission and fusion are two sides of the same nuclear coin. They both involve the manipulation of atomic nuclei to release energy, but they do so in very different ways. Both processes involve the atom's nucleus and release tremendous amounts of energy, which can be harnessed for various applications, from electricity generation to medical treatments. However, they have key differences. Fission splits heavy atoms, such as uranium or plutonium, into smaller atoms, releasing energy in the process. On the other hand, fusion combines light atoms like hydrogen to form a heavier atom, such as helium. This process is the same reaction that powers the sun and other stars. Fission produces radioactive waste, which poses significant disposal and environmental challenges. This waste remains hazardous for thousands of years. Fission is currently used in nuclear power plants around the world to generate electricity. It is a well-established technology with decades of operational experience. Meanwhile, fusion research is ongoing, with scientists striving to replicate the sun's energy production on Earth. This research holds the promise of a cleaner and virtually limitless energy source. Fission is easier to achieve but produces hazardous waste that requires careful long-term management. The technology is mature, but the waste issue remains a significant drawback. Fusion, while cleaner and producing much less radioactive waste, requires immense energy to initiate and sustain the reaction. This makes it a challenging and expensive process to develop. Both processes have the potential to power our world, offering a significant source of energy that could reduce our reliance on fossil fuels and help combat climate change. However, they come with their own sets of challenges and benefits. Fission is reliable but problematic due to waste, while fusion is promising but still in the experimental stage. The future of energy may well depend on advancements in both these fascinating fields. Section 5. The nuclear impact, energy and beyond. Nuclear reactions, both fission and fusion, have a profound impact on our world. These reactions are at the core of some of the most powerful energy sources known to humanity. Fission powers nuclear power plants, providing electricity to millions. These plants are a cornerstone of our energy infrastructure, ensuring a steady supply of power. It also has military applications in nuclear weapons. The destructive power of fission has been harnessed for defense, changing the landscape of global security. Fusion, while not yet commercially viable, holds the promise of clean, nearly limitless energy. Scientists around the world are working tirelessly to make fusion a reality, envisioning a future where energy is abundant and sustainable. Understanding these reactions is crucial for our technological advancement and for addressing global challenges like climate change. By mastering nuclear reactions, we can develop new technologies to reduce our carbon footprint and mitigate environmental damage. As we delve deeper into the atom, we unlock the secrets of the universe and discover new ways to harness its power. This knowledge not only advances our scientific understanding but also opens up new possibilities for innovation. The future of energy may very well lie in the heart of the atom, in the delicate dance between fission and fusion. As we continue to explore and innovate, the potential for a new era of energy is within our grasp.